Don't want to have people on camera if they don't want to be. So, apologize for Thursday's class. Kind of had to do a last minute cancellation. My last half week to week has been a nightmare. I think I'm running on 2.5 hours of sleep today. So be a little bit kind to me today. I think I'll be all right. Got enough caffeine going. But I put up 2 videos on the YouTube. So it was like replacement videos for this class. So once again, I know the link is like in the first week of slides and it's in the syllabus, but honestly, just search Professor Landis on YouTube. My smiling face is right there. We don't want to listen to me. And here's kind of those 2 replacement classes, right? So here was last Tuesday's class, but here's the kind of videos I recorded last Wednesday to replace class on Thursday. I broke it down into 2 parts, so it's really still one class. The topics were disjointed enough to where it made sense to make it into 2 separate videos. So we really started out talking about linear regression a little bit last week, just kind of dives deeper into it. Hopefully it's a lot of review, very simple linear regression, so just a lot more interpretations of coefficients, how these coefficients are very similar to what we were doing when we were taking a sample mean. So I'll kind of review some of this as we cover material here this week. But I'm expecting that you've kind of at least listened or watched these kind of when we start out today, okay? Any questions for me before we kind of dive into material for this week? Hopefully this won't happen at all the remainder of the semester, okay? This is very, very not something I like to do. So, but honestly, I really like this one. This was a really good, this part 1, I think really kind of ties together what we're doing really well in terms of the sampling distribution. So we'll talk a little bit more about linear regression today. I've got week 4 lectures in here. It's kind of a spillover from what we didn't finish. I didn't finish in those videos last week and going into week 5. So I might change that heading. I think the actual file name, if we look at Canvas, is week 5 slides. That's what we'll be using today. Finishing up what I was kind of had in the week 4 slides from last week, and then kind of diving into the next material. Got a do file up there, which we'll kind of dive into at some point, and then a data set that we'll use as well. Okay. So any questions for me before we kind of jump into things here? I'll go through some more housekeeping stuff at the end too, in terms of like a quiz and a problem set that we have. So before we do dive in, I do want to mention, because I was talking to my GA, so part of what I try to do is have the GA TA for this class get practice grading these problem sets, the skill that they're going to need once they have their own class. So it might be a little bit slow on this first one. I've talked to them. They should start working on these. Well, they should have started yesterday. So you might start seeing comments pop up on that problem set number 1. From them, they're going to kind of add comments as they grade it as to why you missed points or why you were credited points for different parts of those problems. That's going to be the same thing I do for every problem set from here on out. Should be a little bit quicker after this first problem. So like I said, they're still kind of getting used to like grading on Canvas. So I'm walking them through that, but you'll see those comments start to pop up. If you have a last name that starts closer to Z, it might just be a little bit later than if it's closer to A, okay? Any questions for me before we dive in here? Okay. Oh, this is not update. It didn't. So we're going to pull open, drag and drop these before I started class today. There was one slide I wanted to introduce the idea with before we talked about heteroscedastic errors. And for some reason, I must have just not copy pasted it quite right. So we went through this. Oh, here we go. So before we talk about hetero and homoscedastic errors, and I'll paste this slide into the week 5 slides that is currently up. So here, right? When we have this simple linear regression, we're going to have some issues that arise from this. So we kind of already alluded to some of it. So what if I think about like the effect of time studying on your exam performance? What do you think is true about the effect of the first few hours? It's going to be pretty large. By the time you study 50 hours, what's the effect of studying a 51st hour? Really small. It's likely not a linear relationship. It's likely it has some curvature to it. So when we try to estimate these linear relationships, we're assuming that we have these conditions. Now, I'm not going to test you specifically on these, but I'm going to mention them, and we'll see kind of how they're violated with different things throughout the semester. So the first one is we're kind of assuming that our errors. So remember, we had this line of best fit. What was the error? For each observation, it was the difference between the actual y and what? Yeah.
estimated one.
Yeah, so when we were coming up with this line of best fit, we had like this scatter plot of data, and we were saying, we'll minimize the sum of the squared errors to come up with this. We're not just eyeballing it, right? We talked about, there's some calculus behind the scenes that stated us for us. But for any one observation, the difference between the actual Y value and the predicted Y values that come from our line of best fit or our linear regression equation, that's going to represent the error that we're making. So on average, if we have this linear equation, this line of best fit, on average, we're going to have errors that are negative and errors that are positive, such that for any value of X here, the expected value of the errors that we're making is going to be 0. Okay, so we're going to have sometimes we're making positive errors, sometimes we're negative. On average, our errors are 0. That's a good thing, right? We want our predictions to be as close to the actual values as possible. So we want the expectation of those errors to be 0. In order for this to be true, and some of the other conditions that we'll dive deeper into later in the semester, we also say we need X and Y to be IID, or identically and independent distributed. So this is just the idea that we're randomly selecting these observations, right? How would this be broken? Well, let's say I'm interested in effort and performance on tests, and the people in my data set, I'm only selecting people that got A's in the class. Okay, well, that's not independent, right? You're going to end up in my data set if you did well in the course, right? Depending on the values for one of those variables. So we want these to be truly random. We're going to say we want large outliers to be kind of unlikely. And what exactly does this mean to us? Kind of hard at this point to talk about. Later on this semester, we'll dive deeper into this, but this is just the idea that we don't have any like one observation that's driving our estimates. Right? So we have one really extreme outlier, like we tried to estimate the relationship between years of education and income, and I throw Bill Gates in there or someone, it's going to skew my results if I only have like a sample size of 30, right? That one observation would really influence. We don't want that. And then kind of the last one, we can't have all of the X values be the same. So if you kind of think about Y, if I'm trying to predict the relationship between X and Y, if Y is changing all over the place and X is always the same value, when I try to make a prediction by plugging in the X value, I mean, I'm always going to get the same Y, and my Ys are over. That's not going to work, right? I need to have some variation in those X values. Okay. So one of the things that we'll focus on today, kind of that first point. So we want the errors not only to have an expected value of 0. We're assuming that that IID assumes that they're normally distributed. Okay. So what is this going to look like? Pulled some textbook stuff, and then we'll come back to this. So what we're really saying is we want the variance on our errors. So we already have that expected value is equal to 0. That's because we're choosing the line of best fit. That's what should be true. But on top of that, we also want the variation that exists in our errors, right? We have this line of best fit. Some observations are below, some are above. We want those errors to be normally distributed, right? Not only do we want them to be normally distributed, we want for different values of X, for the variation in those errors to always be the same value. It doesn't have to be 0. The variance doesn't have to be 0 here. It just has to be the same value. So for different values of X, if we conditioned on, say, 15 as our student-teacher ratio, this is the example I had here was test scores and the student-teacher ratio in the class. No matter if the class is 15, 20, or 25, notice here the distribution of kind of the errors that I'm making. They're all like the same width. They all have the same variance. It's some constant value. Now, what would this look like if this was broken? So this is what we would call homoscedastic errors, right? Homo meaning the same. Heteroscedastic errors is there's variation, right? So if we're looking at different values for X, when I look at extremely low values, maybe there's not a whole lot of variation in my errors. But when I'm looking at really large values for this student-teacher ratio, notice what's happening to this distribution. It's getting wider, which tells me the variance is going up. That means that the variance of my errors depends on the value of X. We don't want that, right? So we won't dive deep into the math behind why. But if we have homoscedastic errors, typically our standard errors that we see reported from Stata are going to be a little bit larger, right? So we can kind of think about why that's a good thing. So I don't love the way I phrase this in the slide, so I'll kind of say the opposite, right? So anytime I have heteroscedastic errors. So this was that kind of second graph where, like, depending on the value of X, the variation of my errors was wider, right? So if that's the case, my errors are going to be smaller. And when I say errors here, let's think about these as standard errors, right? So when we had that stata output, remember, it would give us a coefficient. It would also give us a standard error. That's how we were computing our test statistic. Now, technically, we're always subtracting the assumed true value of that coefficient, right? But when we're thinking about a simple linear regression equation, beta 0, beta 1 times X, what do we always assume this value was? So we always start assuming that there is no effect or that this is 0. So we can kind of ignore this, right? So what happens if I have heteroscedastic errors, which is going to cause my standard error estimates to be a little bit too small, right? So if it causes my standard errors to be too low, what's going to happen to my test statistic? Well, if my denominator's smaller, my test statistic will be larger, right? If my test statistic is larger, what's happening? It's kind of my area to the right. Now, technically, this is half of my p-value, but right, just thinking about the directional changes, what's happening to that p-value? It's getting smaller. So this causes this, causes this. If I have smaller p-values, when do I reject? When the p-value is less than alpha. So is it more or less likely I reject? More likely. So when we have heteroscedastic errors, if we don't do anything, we just treat it as though we do have homoscedastic errors. That's kind of like the default assumption that our variance on the errors is always the same. We're actually going to end up rejecting the null more often than we should. So we're going to be able to say that there is an effect between X and Y, when in fact, there might not be, right? We're going to end up rejecting sometimes when we shouldn't be, okay? So we want to correct for this, okay? That's the end of this. That's the end of the story, right? Is that we know that the heteroscedastic standard errors will be smaller, which kind of has this cascading effect, right? Making it more likely we're going to end up rejecting the null, okay? Any questions on this before we keep moving? And this will apply to if we have a regular X variable, if we have a dummy variable, which is what that video talked about, it doesn't matter, right? As long as we have heteroscedasticity in those errors, it's always going to be more likely we reject. And we don't want that, right? We want to be making the correct rejection decision. So here, I think I had here, this is why I didn't really like this. So it says, this says the homoscedastic errors will typically be larger. And then I kind of outline what that means if the errors are heteroscedastic. So if I'm being, nitpicky, if the errors are heteroscedastic, then the following will apply, which is what we kind of worked through up here in the document. Okay. So just to kind of give you some more visuals to this, if I was looking here, if I try to draw a line of best fit, a linear regression equation, so best fit this data, does this look homo or heteroscedastic? So if I had a line that kind of best fit this data, what's true about the variation of the observations from that line when the X values are low? It's a pretty wide range, right? If I'm looking over here, if I had a line that best fit this data, what's the variation there? Not quite as large, right? So this is going to be something I probably have some heteroscedasticity in my error. So they were actually talking about homelessness in the little flyer thing, right? So if I have unemployment rates and median household income, and I'm trying to estimate that relationship, looks like I've got heteroscedastic errors, I'm going to be more likely to find a relationship between these two variables. And I don't want it to be more likely, I want it to be accurate. Right? So what about something like this? Well, now if I try to draw a line that best fits this data, I don't know, it's a little bit different, right? But it looks like at every point, there's kind of like the same band or the same width of that band from my line of best fit for all values of X. So here I think I had some COVID data, percent vaccinated household income. Well, here it doesn't look like there's much heteroscedasticity at all. This is pretty homoscedastic. I probably don't have to worry about making the wrong rejection decision. Okay. Is that making sense before we keep moving? Okay. All right, so repeat slide. We're going to see how we do this. Data. So I think here, yeah, we'll go off last week's do file. So this was just that regression in class that I was using last week. We got through all of this except for, we didn't talk about heteroscedastic errors. So it looks like the data that I'm using is this COVID data. I've got my global path set up here. Once again, kind of figure out where yours is. It makes it easier to kind of follow along in class. If it's easier for you though, you can always just have the data file, which was this birth data. No, it wasn't, which was this COVID county data. You could just open this up if you wanted to. I'm going to use my global path because I'm switching between computers and I always forget exactly where it is. So I've got this COVID county data pulled up now. Once again, you can always go to File, Open, find wherever. Oh, I might not even have it. There you go. Find wherever it is at on your OneDrive, and you could just open it up here as well. Okay. Any questions on that? So it is beneficial if you can work along with me, which is why getting these kind of data files downloaded when I put them up on Canvas and kind of following along with the do file can be helpful. Right? Also, I saw a couple of you kind of stop by for that first problem set on Friday, so hopefully that was beneficial. I'll echo his thing. Show up to office hours. It's going to make these problem sets a lot easier. I'm always willing to kind of help you, right? So here is some simple linear regression stuff. Went through this in the videos. We're going to scroll down some dummy variables. Here I've got kind of this weird kind of example, but you can start to use like those scatter plots. Oh, there we go. So this is one of the ones I showed you where I was like, oh, this kind of looks like it's homoscedastic, right? If I draw a line that best fits this, the variation of my errors is always about the same. Whereas that unemployment rate and household income, this was also in the slide, that's the one that looked like it was heteroscedastic. Okay. So I'm going to come down here and I'm going to run this regression where I want to try to estimate the relationship between cases per person, right? And whether or not, what percent of the county is vaccinated. And I think this is per 1,000 people. So I'm going to run this regression and kind of say, okay, here's my coefficient estimate. So how would I interpret this? So remember, our coefficient estimate is always a 1 unit change in my X variable. So what's my X variable here? The percent of the county that's vaccinated. So if it goes up by 1%, the predicted number of cases actually goes down by about 1/4 of a person. Okay. So about you might expect that intuitively. Now, if I think about my standard errors here, right? I don't really have to worry about them because it looked like this was pretty homoscedastic, right? Now, if I run this command, which is ESTAT, so STAT, and then IMTest, this is going to basically be a test for whether or not the errors are homoscedastic. So we always kind of start out assuming, just like we assume there's no effect, and if we reject it, right? So here, I very strongly can reject that the effect of 1% more vaccinated in your county is 0, right? The p-value is basically 0, so I can very strongly reject. This IM test is going to be a slightly different test, but it's going to give us a p-value, and we make rejection decisions the same way. If that p-value is less than our kind of benchmark alphas, we're starting out assuming the errors are homoscedastic. If we can reject that, we're saying we found evidence they're heteroscedastic. So we'll run this test. You can kind of see what that output looks like. Notice it does test for other things as well that we're not really going to dive into or use, but we have talked about them. It tests for is there skewness or if there's kurtosis in the data. We're specifically going to be interested in the test for heteroscedasticity, right? So whenever you want to test for something, we want to know, is there an effect from linear regression? We started out assuming no effect. If we want to test for is there heteroscedasticity in our errors, we start out assuming homoscedastic, right? The exact opposite. We stack the deck against ourselves. So here I've got a p-value of 0.07. So that assumption that the errors are homoscedastic, I could actually reject that at what levels? So that p-value is going to be less than what? So be careful. Yeah, 0.07. Is that going to be less than 0.1? Yep. So when we're making these rejection decisions, and I think I did this in the video, but it's always good to kind of see things more than once. We're going to kind of bounce back and forth in between these different terms. So the easiest one, I think, is to think about confidence levels, because that's kind of lines up with like confidence intervals. So we're saying things with 90, 95, and 99% confidence. Now we can choose different levels, but these are our three benchmarks. Those would correspond to what levels of significance? 10, 5, and 1%. Right? So my alphas are essentially my significance level, just in decimal form. So 0.1, 0.05, 0.01. So we know that we can reject the null if the p-value is less than alpha. Remember, what is our null now? Is that the errors are homoscedastic. Now we can write this out technically, but I'm always just going to ask you if you can reject if they're so. If you want to use words here, that's fine, right? Really what we're saying is here is the variance of our error term for different values of x. Is it always the same value? But we can write out in words here because we're not going to be super technical in terms of the math. Right? So is my p-value of 0.07 less than 0.1? Yep. So I can reject that the errors are homoscedastic at the 10% significance level or with 90% confidence. Now I can't reject it at the higher levels of confidence, right? So at higher levels of confidence, I can't actually say that I found strong evidence that they're heteroscedastic. I only really found it at that 90% level, okay? But 90% isn't nothing, right? So how do I account for this, right? I know that when they're heteroscedastic, we said it's going to be more likely I reject, right? That p-value is actually not, I see from my standard or the p-value I see from my linear regression equation isn't quite right. Okay? So we'll go back and say, okay, here was one where it looks like, we can reject their homoscedastic only at one level. I think I had a different example down here. Nope, it's the same one. So we kind of just talked about this. What I can do is use one of the following commands, right? So if I reject that the errors are homoscedastic, even at one of those levels, I have some evidence they're heteroscedastic. I want to not solve this. I want to account for this, right? I want to basically make sure I'm getting the correct standard errors and the correct rejection decision. So if you add in this kind of VCE robust or just the robust command after you run this regression, what it will essentially do is account for the fact that you had heteroscedastic errors, right? And it'll give you the standard errors you should have found if instead these were homoscedastic errors, okay? So either one should provide us with the exact same new standard error, which compared to before, so 0.021 goes to 0.022. So it didn't increase by much, but our standard errors for that homoscedastic are a little bit larger, right? Our heteroscedastic errors were a little bit smaller, which increased our test statistic, made our p-value smaller, made it more likely we could reject. Now, once again, not much, right? And other examples that can actually influence it by quite a bit, right? So here we've got our kind of corrected standard errors, our corrected test statistics. So instead of what? Negative 11.73, it's a little bit smaller in magnitude, a negative 11.48. Now here it doesn't matter. Our p-value is still 0, so we still make the same rejection decision. But if it was a little bit closer to those cutoffs, you can imagine it might push us kind of to one side or the other. Okay. I think I have an example here in a second where it'll do that. So this IMTest command is your way. You're not just going to eyeball the data, right? You use the IMTest to determine, do you have evidence that there are heteroscedastic errors? Can you reject the errors or homoscedastic? If you can reject, then I should be using this robust command, right? And I should be kind of accounting for that, right, in my regression. Okay. Any questions on this? Yeah.
What would happen if you used like the robust command, even when it was not necessary, like there was no?
So in theory, do you think anything is ever truly homoscedastic? Even if I can reject at the 1% confidence level, right, which is like a very low level, there is going to be some level where it is, I mean, it's never going to be true. No data set would you have perfect homos. So it can still update it for you. It's just in general, we don't worry about that because we aren't rejecting the errors. Like we didn't have evidence that they were, so why are we trying to account for it? You could end up with a scenario where if it was low enough, it actually flipped your rejection decision the other way, where it made it. So here we're thinking it's more likely we reject, so we might not reject now. If you had like really low levels of confidence, it could do the reverse. I wouldn't expect you guys to know that, but it's a good question, right? We really only want to use this robust command if we have evidence from this IM test that we do have heteroscedastic errors. Is that what you were getting at? Now, in practice, with really large data sets, just like with the coefficient, this is where I think it's good to like rehash some of these things. So if I'm thinking about the distribution of my slope coefficient, we said, you can kind of think about it. We've got the estimate, we've got our standard error, which is like the sum of y minus y bar squared over n minus 1. So when we have higher sample sizes, what's happening to our standard errors? They're going down. Our test statistics are getting higher. So the same thing would apply not just for slope coefficients, but for this IM test. So with really large data sets, it's almost always going to be the case that we can reject that the errors are homoscedastic. So you'll see, like in practice, if you look at like academic papers, almost all the time, they just throw in the robust command. As long as you got a pretty large data set, you almost inherently know that your p-value for that IM test is going to be small enough to where you can reject that the errors are homoscedastic. Does that make sense? Once again, these are good questions, probably pushing a little further than I would expect, but this is good. Okay, so you can look at another example here. I think I've got kind of this dummy variable one. So here I'm kind of estimating whether or not what the relationship is between is the county considered a metro county or not, so just 1, 0. And then the X variable I have is what was the unemployment rate. So how would we interpret this slope coefficient? So anytime I have a dummy variable as my Y variable, the change in my X variable is still 1 unit. So if the unemployment rate goes up by 1%, that's how we measured unemployment rates. But if my Y variable is just a 1, 0, changes in my Y variable will be changes in what? What would the units be? Watch that video. What did I say? Dummy variable changes in the units would be changed in the probability. So if the unemployment rate goes up by 1%, the predicted probability that it's considered a metro county would decrease by 0.04. Okay? So this must mean that what? Metro counties, when unemployment rate was high, they were just not as likely to get vaccinated, or people weren't getting vaccinated as much. Not wildly, surprised by this, right? So, just to kind of get some more practice doing these interpretations, I threw in this dummy variable one. Now you'll kind of notice here, if I use this robust command, here we kind of have a weird one. So 0.00459, 0.0042. This actually made my standard errors a little bit smaller. So this goes to the point, if I run my IM test here, I can't actually, so we'll go up here just to kind of remember what that looked like. Whatever regression I run, oops. So I said, usually when we account for this, it should make it such that our standard errors are a little bit larger now, right? The problem is, if I run this, let's see. Right? So actually, wait, no, it did make our errors. Am I looking at this wrong? It went from 0.0042. Yeah, it did make them a little bit larger. Sorry. Yeah, so this will make them a little bit larger. And why? Because we rejected that they were homoscedastic at really high levels. Right? So this one kind of follows along with the same type of example we were just working through. If we reject this, using this IM test, we can reject that they're homoscedastic. When we account for this and use that robust command, it should make our standard errors a little bit higher. Not much here, 0.0045 instead of 0.0042, but a little bit higher. Okay. Which, if our standard errors are higher, our test statistic is going to be a little bit. So where's the standard error? It's in our denominator. So if our standard error is smaller, our test statistic will be. Our test statistic is larger, our p-value is smaller. It's going to be a little bit more likely we can reject. Okay. All right. Let me think if there's anything else I want to say here. Where are we at in time? 40 minutes. I'll show you a different way, just to kind of some more stuff in Stata. I'll probably only do one of these examples, but I think it's worth thinking about what we're doing behind the scenes. So if I run this regression command, so I go back to where I was kind of trying to understand the relationship between the number of cases per person and the percent of the county vaccinated. Anytime I run a regression, so I have that same coefficient that we had earlier, I can use this predict command, right? So if I run this predict command, it's going to predict whatever that y value is, right? So for various value, whatever the observation has their value for x, it'll essentially give you the predicted y. So if I have the actual y, and I now have my predicted y, what could I also calculate? What's the difference between my actual and my predicted y values? We call that my error, right? So that's my error term. So here, oh, there we go. If I wanted to calculate my error term, and I take the cases per 1,000 people, that's my y value, I'm now going to use this predict command. And what this will do is, essentially, it'll use the slope and intercept coefficient. So for every value, it's making what the predicted y value should be. So you could do this by hand, right? You could use the slope coefficient estimate and the intercept, and you could go through, plug those in for every observation, make your predicted y value. This predict command will just automatically do it for you. So notice, if I run this regression and use the predict command, I then go look here, it'll create a new variable. And I called it predicted cases. So the actual number of cases, right, it's a little bit off. Some of them it's a little bit more off than others, right? So this is a very quick and easy way I can come up with the predicted y values for every observation. Any questions on that before we keep moving? Yeah.
Should our values be different than yours? If I have predicted cases.
So like the coefficient estimates?
Like I just have different numbers. Like, yeah, I don't have like 42 point.
Oh,
Yeah,
probably. So up here, it might just be that the data is sorted differently. So because I think I did some by sort commands and the other, yeah, so you might still have it sorted by, so yeah, anytime so that's a good point. That's a very good question, actually. Whenever we view this data, this just shows me a snapshot of the data. I happen to have this sorted by county FIPS, it looks like, but it can be sorted by any variable in this data set, right? In fact, let's say I wanted to know what county has the largest population. I'm not sure that I've shown you this command because I really had a use for it, but to make sure that we're getting the same values. So let's say here, well, let's find out what county has. So if you use the sort command, so I'm going to run this regression, sort data, and then predict. Well, I've already predicted it, so I can't recreate that variable. But if I sort it by population, if you did the same thing, now you should have the same order of the observations as I do, and then you should have the same predicted cases. Yep. Yeah. So it's just that depending on what we do, sometimes the order of the data, when you run regressions and things, it changes where those observations are. It's the same data set. It just changes the order in which it's being shown to you in the viewer.
And does it automatically sort to ascending?
I forget what it defaults to be completely honest with you. Honestly, some of the times when I give you the data, it might not be sorted by anything. It might just be however I downloaded it, wherever the data source existed. Sometimes it's not sorted. If you do want to sort it, you can always use that sort command. Notice why is it kind of, oh, I guess here,
Yeah.
we know what it defaults to, right? Because I just used it. What does it default to? Smallest to largest, right? There's like some ways too, you can like, I think it's here. No, I don't want filter, sort, and then you can change it. Like this is like a little bit more like user friendly. There's some commands and I forget what they are off the top of my head. In fact, you could do something like data sort. Let's say we want to make sure it's, so we're gonna do population. And we want form equals standard sorting, advanced sorting. And we want, I forget how to exactly do it. There's some command. You could probably Google it real quick. You throw something else on the end of sort and it will do it descending instead of ascending, right? I think you have to actually use like a G sort. I wasn't planning to show this to you guys, so I forget exactly. I think G sort is the one. It's a slightly different command where you can change like which way it sorts it. But that's why if I'm viewing the data, it might look a little bit different than you depending on how it's sorted. But this is kind of helpful. Notice like, what's the largest county? LA County. What's the smallest county in this data set? Someplace in Texas. Or I'm guessing West Texas somewhere. Okay. So that was a good question. So we've got our actual Y values and our predicted Y values. How could we create the error term? Well, we said the error is just going to be, and now I forgot where I was at. Here it is. The difference between, what did I forget here? I'm creating a new variable. So I want to generate this new variable, call it error term, take the actual Y and subtract that predicted Y value I created. Okay? So all that's going to do is in my data set, take the actual Y, subtract the predicted Y. When my prediction is too high, I'm going to have a negative error term. When my prediction is too, where's an example where it's too low? Right here, I'm going to have a positive error term. Well, now that I have the error terms, what's one thing I could check to see? So one of the assumptions that we talked about earlier, I said the error term, my assumption is that for different values of X, the expected value of the error term should be 0, right? Now, we can't quite get at that like for every single value, but if I just look at the sum of this error term, e to the negative 8, I think, what did I say that means? Move the decimal 8 places to the left. So this is basically an expected value of 0, right? So our error on average here is expected to be 0. That was one of those, that's good. That was one of our assumptions we want. Right? Now, what I could also do is skip these intermediate steps. And when I run, oh, here we go. Whatever the last regression I ran was, so I don't have to like keep rerunning this regression. Whatever the last regression was run, that's stored behind the scenes. You can't actually see it. So it's got the slope and the intercept coefficient stored behind the scenes. That's how it was using that predict command to come up with the predicted Y values. What you could also do is use that predict command, but create a new variable, which you call residual. So we'll start using these two, they're synonymous terms. The error term is sometimes referred to as the residual, right? Why I forget exactly when. It's like more often as people call it the residual, some people call it the error term. I think residuals might be a little bit more common in like math, whereas error term might be a little more common in like the social sciences, econ, things like that. But people use them interchangeably. It's the same thing. So if I use that residuals after predict, it will create essentially what I just created, that error term variable. So we can go ahead, run that. Now, once again, I don't have to rerun the regression. It still has it temporarily stored there, whatever the last regression I ran was, okay? So now when I look at this data, notice my error term and my residual, that's the exact same value. And I'm just skipping a couple steps there, right? So if I want to see every step along the way, there's always longer ways to do things. Quite often, there's also a shortcut. Right? Now, what would tell me, excuse me, if I've got kind of hetero or homoscedastic errors? Well, essentially, if I'm looking at the residuals or the errors that I'm making, if those are correlated at all with kind of the predicted values for Y, right, that might tell me I've got some heteroscedasticity in my error term. So I could use like a scatter plot and think about okay, it looks like when my error terms are positive or negative, what's true about the predicted values for y? It looks like they kind of have the same range. Maybe they're a little bit more narrow for my positive errors than they are for my negative errors. So maybe there's some heteroscedasticity going on here. But if you look at that correlation of those errors that you're making and the actual predicted values for y, this should also kind of give us some evidence of whether or not they're homo or heteroscedastic. I won't likely throw a question like that on the quiz or on your problem set. I would just expect you to use that IM test, and then kind of knowing that, can you use that robust command to correct for those? But this is another way of thinking about it, right? And it also allows us to revisit the idea of what the error term is and things like that. Okay. Also, it allows me to kind of show you this predict command, which will have a lot more power when we start doing multiple linear regression. For simple linear regression, it's just one variable, one slope coefficient. When we use multiple linear regression, we're going to have multiple, right? So it can do some math a lot quicker for us. Okay. I had another example in here. I don't think for the sake of time, we won't go through it in class here today, but it's a very similar thing. You could kind of do the same thing, look at, come up with your predicted values for that y variable, use the residuals, kind of graph those, or the residuals of those error terms against those y values and see, does it look like here? Oh, well, this one looks like a little bit easier, right? I mean, for really high errors, what's the variation in my predicted y values? Pretty small, right? What's the variation that exists in my predicted y values when the error is negative? Much larger, right? So I've got differences in the variation of these error terms. Right? But the IM test is really the gold standard, right? This is just a way to kind of visualize what's going on. Okay. All right. Any questions? I think I did some of this stuff did this at the end of part 1, kind of looking at that sampling distribution. So it should be everything we need from Stata for right now. Unless there's any other questions, we'll kind of jump back the slides here. Okay with this? All right. So hopefully we got some of the basic tools out of the way. We're now going to dive a little bit deeper into some much more meaningful regressions, right? So some of the assumptions that we made, those kind of 4 assumptions I was showing you earlier, it's kind of what we call our ordinary least squares assumptions. So when we're running these simple linear regressions, we had those 4 assumptions. The expected value of the error term was 0, IID, no large outliers, and what was the last one? I'm already forgetting. Top of my head, which order did I have them in? Oh yeah, so that one's a little bit different for the simple. So you can't have X be all the same value. Eventually, this gets changed a little bit with multiple linear regression, and it makes a little bit more sense because, like, why would you have a data set where X is always the same value for everyone? That seems kind of weird. But with multiple linear regression, we run into something where that's a little bit different. Okay? So if we have pretty significantly large sample sizes, I mentioned earlier, we don't, more often than not, we can reject that null that the errors are homoscedastic. But as our n gets higher and higher, there's also something else that applies, right? So when we're looking at these sample coefficients, what distributions do they come from? Not a standard normal. They actually come from what? Because it's sample data, student t. Now we said, as I get larger and larger sample sizes, in fact, if I can get over 100, out to like the 3rd or 4th decimal, the difference between my p-values from a student t distribution and the standard normal are basically the same. So with really large sample sizes, my student t essentially becomes my standard normal distribution, right? It's a very close approximate. The same kind of thing would be true if I'm thinking about my errors, right? If I have heteroscedasticity in my errors, when does that matter? When I've got lower sample sizes. As I get larger and larger sample sizes, the difference between the errors I see for my standard error for my homo or heteroscedastic errors essentially goes to 0. So once again, large sample sizes save us, right? Even if we don't include that robust command, we're likely going to be making the correct rejection decision, right? We don't even have to account for the fact that there's heteroscedasticity in the errors, because with large sample sizes, those two things become approximately the same, okay? And which is why when we were looking at the data, right, we were dealing with what? 3,000 observations. So even when we were looking at that standard error and we were saying it was changing, but only out to like the 4th or 5th decimal, it's because we had a really large sample size, right? If we had smaller sample sizes, we could expect those differences to be a little bit larger. And then it really would matter that we use those robust commands. Okay. So some of the same sort of principles we'll start kind of reapplying. You know, we talked about larger sample sizes, kind of bringing that student T closer to the standard normal. Larger sample sizes, we kind of bring those standard errors we see from the heteroscedastic error variable closer to what if it was actually homoscedastic. Okay. So always try to get more observations, right? It's kind of the end of the story there. So we're going to transition a little bit away from the error terms, thinking about correlation and causation. Okay. So I like this stuff. It's a little bit more intuitive and it's kind of fun. So I'm not going to waste a ton of time on this because I already showed these to you. So let's say I run a simple linear regression, right? Why might this assumption, oh, let's think about this one here. Why might this be kind of invalid, right? So this is saying if I'm trying to predict wages from marijuana usage, that given different values of that X variable, which is marijuana usage, my errors in the predicted wages might be something other than 0, right? So this might be something when I have, you know, individuals using almost, you know, using 0 marijuana, maybe my predictions are really accurate, right? However, when I have larger amounts of, well, some people are very effective using marijuana every day. Some people become bums, right? So I'm going to start to get a much different variation, even a different mean expected error term when the values for that X variable are high. So what's kind of driving that X variable to be high and what's driving the Y variable to high? There's other things going on. It's not just these two variables, right? When I'm trying to predict, I'm going to skip ahead here. Let's say I was trying to predict the number of crimes in a county based off of, and we'll just get rid of this for a second, just the number of police officers. I am going to find a very strong positive slope coefficient here if I just run this simple linear regression. Why? Areas that have high crime, well, they're likely to have higher number of officers because those areas are also likely to have more people, right? If we don't account for the population of the county, there's likely these other factors that are driving both of these variables. And if we don't control for them, it could very well be that when we just estimate this simple linear regression, the effect of the number of police officers in crime, it's picking up the effect of all these other things we're not controlling for that are correlated with our X and our Y variable. So anytime we have omitted variables that might matter, so that might impact our Y variable and are also correlated with our X variable, it's going to cause our estimates to be what we say are biased or wrong, right? So when we're running simple linear regressions, we shouldn't put a lot of stock into them because we're likely not controlling for a lot of other important factors. But good news, we can control for them. You can just add them into that regression equation. Now, it's hard to get a visual. So when I had one X variable, one Y variable, I could show you this line of best fit. If I have two variables, well, now I need another dimension. Now my line of best fit is like 3-dimensional. If I have another variable and I've got now it's 4-dimensional, I can't give you a very nice visual, right? But we can still do the mathematics, right? Because what I'm doing is still the same thing. Even when I include more variables on the right-hand side to try to predict Y, so I know that the number of police officers is not the only thing that mattered for crime. Population mattered, probably the area of the country mattered, the average income in that county probably matters. I want to include all these other variables to try to predict what the number of crimes will be in that county. Well, I'm still going to choose a line of best fit. I can't visualize the line now. It's just like 6, 7, 8-dimensional line, right? But I'm still going to choose the line that minimizes the sum of the squared errors. So we still want to be making as accurate of predictions as possible. We want to over penalize really bad errors, right? That's where that kind of square came in. But when I start to rewrite this out, it looks the exact same as what we were doing in simple linear regression. It's just now our predictions. There we go. Include not just one X variable, they include all of them. So now I've got an equation, I'm trying to minimize it. But now I can choose not just the intercept and the slope. I can choose the intercept, slope 1, slope 2, slope 3. I have n equations. Well, however many variables, we'll call that n. so n plus 1 unknowns. I could take a derivative of this function in respect to each one of those coefficients, n plus 1 unknowns, n plus 1 equations. I don't want to do the math, but I could and solve for what all those should be, right? Stata will do all that work behind the scenes for us, right? It'll basically do all that calculus and spit out at us what those slope coefficient estimates are for every single one of those variables we included on the right-hand side. Okay? So it's the same thing, right? It's just we have more unknowns, more equations. The math's harder. But if we use Stata, math isn't hard for us. Now, the interpretation of these slope intercepts are going to be exactly the same as what they were before. So even if I go back to my very simple one, how would I interpret, if this is the number of police officers in the county, this is the number of crimes, how would I interpret my slope coefficient? For every one additional police officer, I would expect the predicted crime rate goes up or down by whatever this slope coefficient is. It's just when I have other variables, I throw in one other caveat. That's still my interpretation of the slope coefficient, but holding everything else in my regression constant. So holding constant the population of the county. So the thought experiment is like 2 counties, exact same population, but one of them has 1 more police officer. What would we expect their predicted crime rate goes up or down? That's a lot more powerful of a statement. Now here I just have one variable. What if I include the average income and the average age? Well, now the interpretation is holding constant the average age, the average income, the population, but one of those counties has 1 more police officer. What's the expected change in crime? That's a lot more powerful of a statement when I can hold all these things constant. And you don't actually need this thought experiment to actually exist in the data. You're just using the data to be able to make these interpretations that match up with these thought experiments. Do you have a question?
Yes, so holding the other variables constant. And then you're increasing the slope of the variable you want to see the effect of.
Be careful when I say it. It's not a change in the slope of the variable you want to know the effect of. It's a change of 1 unit in the variable you want to know the effect of, and the slope tells you the effect of that 1 unit change. Right? So here, the slope of having 1 more police officer, 1 more unit, the expected change in your y variable is the slope associated with that. Is that? Yeah. Okay. Questions on this before we keep moving? So I want an actual example here. I'll come back. Let's say I have this one, right? I just like, and more right now, I think more interpretations is beneficial. We can dive into kind of what's going on behind the scenes a little bit more, even if we don't get there today. We do that on Thursday. So here I had a data set where I had wages. I think this was annual. No, this is, yeah, this might be annual. No, this is hourly wages. I'm looking at these numbers. This is hourly wages, right? So hourly wages, we're predicting it based on the person's IQ, their age, and the number of years of experience they have, okay? So how would I interpret beta 1 here? So beta 1 is the slope coefficient associated with IQ. So how would I interpret that? So first of all, what's the value of beta 1? What does beta 1 go with? What variable?
8.401.
Yeah, it goes with the IQ variable. If I look at my regression output, what's the slope coefficient associated with IQ? 8.41. How do I interpret that? This is the predicted change in your y variable when that x variable of IQ goes up by 1 unit. IQ is measured in points. So when someone has 1 point higher of a measured IQ, their predicted hourly wage would be $8.4 higher, or whatever. I think this is US dollars. I'm sure this is the data set was in US dollars, right? Now, can I say that that IQ is actually having an effect on hourly wages at our conventional levels? Statistically speaking, what would I look at? That coefficient estimates. What do we use to make rejection decisions? P-value. What's the p-value? Is that going to be less than any of my conventional alphas? It's 0, right? Yes, it's going to be less than like any level, right? For the 99.99% confidence level, we could say that there's a strong effect between IQ and wages, okay? Now, be careful, when we made that interpretation, we left off something. This was the expected change in my hourly wage if I had a 1 point higher on the IQ, but now what do I add in with this multiple linear regression? Holding everything else in this regression is constant. So holding constant the person's age and the years of experience, the effect of having 1 point higher in IQ would be $8.4. Okay. Any questions on this before we keep moving here? So one thing we haven't talked about is how do I interpret the intercept coefficient, right? So before we said the intercept coefficient was the expected value for y when my x variable is equal to what? 0. So now what do you think, how would I interpret that? The expected value for y when, well, when would this be the expected value of y? When every single variable is equal to 0, right? So just a little bit different, nothing too crazy there, okay? Now you'll notice these interpretations for the intercept start to get weird, right? Because is anybody 0 years of age? No, right? But this line, like, you can't visualize it, has to start somewhere, right? So, you know, they won't have like real strong, useful interpretations for us, the constant a lot of the time. But these slope coefficients will have a lot more use. But we can still interpret them. I think if there's anything else I want to say here. Yeah, we'll jump the gun a little bit. We'll come back to this stuff. Where's that? Yeah, we'll come back to this next class. I want to go through this example since we already set it up. And we've got, what, 15 minutes? Oh, yeah, so we got enough time to go through it. So let's go back. So now that we know, like, we should be including other variables, let's think about what happens if we don't. Okay? So I said before, it's likely the population of a county matters. So if I were to run this simple linear regression, where I'm trying to estimate or predict the number of crimes based off the number of officers, I had a small data set here, it was like 92 counties, right? However, just using this one variable of the number of officers, what percent of the variation in crimes can I explain? So what statistic would I look at that we've talked about before? What tells me the proportion of variation I can explain in the y variable? My r squared, right? So what percent of the variation can I explain? Portion I can explain is 0.74%. I can explain is 74%, approximately, right? 74.8%. Okay. Is that hopefully, remember when we were talking about the r squared there? So we've got this estimate that if I have one more police officer, I get more crime. Seems weird, right? But what's likely true in counties that have to hire more police officers? Do you think that Bloomington has more or less police officers than Indianapolis? I hope that Indianapolis has more, right? They have a lot more people. So when I control for population, well, now it's not like I'm comparing Indianapolis to Bloomington. I'm comparing two cities of similar size. So maybe I'm comparing Bloomington to like West Lafayette or Lafayette, whatever, right? So I've got two places of similar size, the exact same population, but one of them has one more police officer. Now the effect looks like it's not even twice as large, right? Now having a police officer only increases the number of crimes by 14, right? So the size of my coefficients can change dramatically when I start to include these additional controls. And that makes sense. I'm controlling for more factors that probably matter. You know, sometimes you guys amaze me. You're so smart, right? So I mean this genuinely. What happens when I start adding in more variables on the right-hand side? What can't happen to the r squared? If I include more variables, at the very worst, my r squared would do what? Stay the same. It might not go up by much. So here it goes up to 82%. right? And maybe it only goes up by 1%, like, but it has to at the very least go up by something, right? The very worst, I threw in a variable that, like, let's say I throw in, I don't know, the number of dance groups in the county. I don't know, something that shouldn't matter when it comes to estimating crime rates. My R squared would just stay the same. It can never go lower. It can only go up, right? I guess like I said, technically it could stay exactly the same if I had like a wild variable in there that had no effect, right? But we probably aren't adding in variables that have no impact, right? So yeah, that's good. Anything else I want to say here? So kind of what we would say here is once we start to add in these additional control variables, we've eliminated some of the bias that existed in our naive regression. How much of the bias did we eliminate? Well, the estimate went from 33 to 14. So we eliminated what? About bias like 17. So as we add in more and more variables, what happens? We can eliminate more and more of the bias that exists. Okay. Now, the bias might not always be that like it's making it smaller. It could work the opposite direction as well, right? It could have been like a negative bias that I'm eliminating. Right? But as we add in more and more control variables, we should be getting a more accurate estimate of what that slope coefficient estimate is. Okay. There was another question. Yeah, there you go.
Yeah, so in the real world, like,
Mhm.
when you're looking at data, interpreting data,
Mhm.
is there like a target R squared that you can get to for it to be like,
Every field is going to be a little bit different. And like, for instance, in economics, when you're working with really large data sets, what do you think that like, and you have a lot of variables available to you, what do you think is probably true about the threshold for R squared? They want to see really, really high, right? If I'm doing like, I was just telling him, my brother's a professor as well. He does like kinesiology and human performance type stuff. They have like sample sizes of like 40 and some of that, right? So for them, our high R squared, they're not going to have near as much data, not as many high of a sample size. Their R squared is going to threshold probably a lot lower, right? But yeah, in practice, when we have these really large data sets, I mean, we want to be seeing R squareds for sure that we're explaining more than half the variation. Because if we're not explaining half the variation, what's going to be true about the bias that exists in our estimates? It's likely there's a lot of it. As I start adding in more variables and I can explain more of that variation and why, what am I doing by adding in each additional variable? I'm eliminating more and more sources of bias. If I can get enough variables on the right-hand side here, maybe I can eliminate almost all of it. So I get like an R squared of like 0.99. I'm not worried about missing anything, right? I think that I'm probably making pretty good predictions, right? But yeah, depends on who you ask, exactly what field. We'd like to see something above 50 for sure. Yeah. These are good questions. Any other questions before we keep moving here? Okay. All right. Just another example to kind of think through these and start to think about the bias that would exist. And we'll dive a little bit deeper into like what the sign of the bias is. So notice here, when I included population, what was likely the correlation between population and the number of officers? Like correlation coefficient or covariance. Probably not a number, but is it positive or negative? Positive. Higher population counties probably have more officers. Higher population counties, what do you think the covariance would be with crimes? Positive. So we had a positive and a positive relationship, and when we included this important omitted variable, it eliminated a positive bias. It reduced the coefficient estimate. The exact opposite can be true as well. So if we think about here, I think I have an example. Let's say I wanted to know the effects of smoking while pregnant. So this is a 1-0 variable. Just did you smoke during your pregnancy or not, right? And birth weights. Birth weights, higher birth weights in general are good. They're a measure of health of the baby, right? So if I were to run this regression, what do you think the sign of that coefficient estimate is going to be? Mothers that smoke while pregnant, probably not good for the baby. What do you think happens to the birth weight? It's lower, right? They're more likely to be premature. Strong negative effect. Now, here's where it's not always that my estimate is going to be kind of like going in just one direction, going from like a smaller value. Here, There could be another one. So why might that actually overestimate the negative effect that exists from smoking while pregnant? So if someone came to you with this, and then I looked at this and I was like, you know what? I bet smoking doesn't actually impact birth weights near as much. Well, why could I maybe make that statement? What's a omitted variable here that you think is both correlated with whether or not the mother smokes while pregnant and birth weights? So alcohol consumption could be one, right? I'm guessing mothers who use cigarettes or who smoke while pregnant are more likely to drink alcohol. And maybe that's positively correlated with smoking, but alcohol consumption would be really what? Negatively correlated with birth weights. In fact, if you look at the data, alcohol consumption during pregnancy is way worse than smoking consumption, right? So it could be that this effect is really being driven by this omitted variable of alcohol consumption, right? The other one I always think about here is what if I had like the income, right? If I have higher income, do you think it's more or less likely the mother smokes while pregnant? We're being a little bit stereotypical, but the data proves less likely, right? So if I were to include income, that would actually be negatively correlated with smoking while pregnant. And having more income, I have more resources to go to like maternal fetal medicine appointments. I have better access to higher quality foods. All of these things would actually cause the birth weights to be higher. Well, now I have this negative correlation with the X variable, positive with the Y. I might actually be getting an estimate that's too low, right? This might actually be incorporating a lot of the effects of actually having higher income. So the actual effect of smoking while pregnant might not just be -50. If I could include that important omitted variable of income, it might be even larger of a negative value. So it can go in either direction. And to the point of alcohol consumption, I didn't think about that one. That's a good one. It would probably push that closer to zero because it is probably capturing a lot of the negative effects from alcohol consumption as well. But all of this goes to point, like, if we have the data, why are we not including it into our regression? We can eliminate all of this bias by simply including all these things like education, income levels, alcohol consumption while pregnant, and then we can get more accurate estimates of these slope coefficients. Yep. I always use this one, right? Just because it's stupid, but like easy to see. So if I look at autism and organic food sales, this is a strong, if I run a linear regression here, this is rejected at every level and it looks like it's highly positively, okay. Organic food sales aren't causing autism rates to rise, right? What's likely correlated with both of these things? I don't know, an increased focus on health, right? Areas that have higher income are probably more likely to get their kid diagnosed with autism, but also more likely to be able, to afford more organic foods. So it's likely that anytime we see that X is causing Y, it could be that there's this variable Z that's causing both of them to change. So I always kind of use the dumb kind of meme here. I used to think correlation implied causation. Then I took a statistics class and now I don't. Well, it sounds like it helped, right? Well, maybe not. Maybe I took the class because I was already going to be more likely to understand this difference, right? So this is outside factor Z, the fact that I was a higher IQ individual, that's really driving my ability to understand this difference, right? Not the fact that I took the class, right? So correlation versus causation, we'll kind of hit this again more in detail on Thursday's class. But before I let you guys get out of here, this might be a fun thing. Maybe you'll just think I'm old and dumb, but I'm going to try to start using, I told my wife that, it's like, how hilarious would it be? And hilarious in a terrible way. If I just like started every class with a catchphrase of like, who's ready to learn? Or like something really corny. Like I was recording those videos. I'm like, what if I like started putting these out on YouTube and I'm just like, it's a great day to learn. She's like, well, let's just start coming up with one for every day and using ChatGPT to come up. So she helped me do this, but today's was going to be, here, I got to get it right because it was look, ChatGPT, don't use it to cheat, but it's likely going to be able to increase like your ability to do things if you use it correctly. So what was the one she gave me? I don't want to screw it up because it's really good. Oh yeah. So today we're doing linear regression because even data needs a glow up. So that was the one ChatGPT gave me. I'm going to try to start using it at the beginning of class from here on out. Maybe draw you in a little bit more. We'll pick up with this omitted variable bias stuff, looking at multiple linear regression on Thursday. I might expect an in-class quiz on Thursday. Other than that, I also put up the next set of practice problem. That next quiz and problem set are due next Tuesday. All right, so start working on that problem set early so you can come to me with questions. And I'll see you guys on Thursday. Try to stay safe tomorrow if the weather's bad.